Hello, everyone. Welcome to our presentation. I'm excited to be here with you today. Today, we'll be exploring the fascinating world of functions and modules in Python. This is the first slide, which is our cover slide. We'll start by introducing the main topic and setting the stage for what's to come. Over the next few slides, we'll dive into how functions work, how modules help organize code, and some practical examples along the way. So, let's get started and explore the power of Python together. Let's take a quick overview of the contents we'll be covering today. We start with the objective of this session, which is to understand the fundamental concepts of functions and modules in Python. Then, we move on to calling a function, exploring how to execute functions properly. We'll look at the different types of functions in Python, including built-in, user-defined, anonymous, and lambda functions. Next, we dive into function arguments, which are essential for passing data into functions. We'll see how to access docstrings to understand what a function does. Then, we'll examine defining functions and the importance of the return statement to send results back. We'll also discuss variable scope and lifetime, highlighting where variables are accessible and how long they exist during execution. Moving forward, we'll explore creating user-defined PACKAGES and MODULES, which help in organizing code effectively. Additionally, we'll look at the structure of packages and how to import functionalities using the from import statement. The presentation also covers introduction to SLM, NumPy arrays and functions, and working with pandas data frames and series for data representation. Throughout, you'll see practical examples, such as array creation, reshaping, and working with datasets, to reinforce these concepts. By understanding these key points, you'll be well equipped to write organized, efficient Python code and utilize its powerful libraries effectively. Today, we're diving into the core concepts of functions and modules in Python, which are essential for writing clean, efficient, and reusable code. First, we'll explore the need for functions, starting with their definition and how to call them. We'll look at how variables behave within functions, what we call scope, and how long they live, their lifetime. We'll also discuss the return statement, which allows functions to send back results to the caller. Understanding how to define functions properly is fundamental to structuring our programs effectively. Next, we'll move on to lambda functions, also known as anonymous functions. These are useful for creating small, throwaway functions without the formal structure of a full function definition. Alongside that, we'll talk about documentation strings, those comments that help us understand what a function does, and emphasize good programming practices, like writing clear, maintainable code. Finally, we'll introduce modules and packages in Python. Modules are simply files containing Python code that we can reuse across different programs. Packages are collections of modules organized in directories, making it easier to manage large projects. We'll also look at the standard library modules, those built-in tools Python provides that save us time and effort. All these topics connect to the larger goal of writing modular, organized, and efficient code, which is key to becoming proficient in Python programming. So let's talk about what a function actually is. Essentially, it's a block of organized, reusable code that performs a specific action. Think of it as a mini machine within your program that does one particular thing. Now, why do we need functions? Well, first, they significantly improve the readability of our source code. Instead of writing the same code over and over again, we can just call a function whenever we need it, making our code cleaner and easier to understand. Another key benefit is code reusability. Once you've written a function, you can use it in multiple places without rewriting the same logic. This also makes debugging much easier because if something goes wrong, you can focus on that specific function instead of the entire program. Functions also reduce the overall size of your code, which is great for maintaining and updating your projects. And, from a broader perspective, they support modular programming, breaking down complex problems into smaller, manageable pieces. So, in essence, functions are fundamental building blocks that help us write efficient, organized, and maintainable code, aligning perfectly with the overall goal of creating better software. All right, let's dive into defining a function. When we see the word def, it marks the beginning of a function in Python. Think of def as the way we tell Python, hey, I'm about to create a reusable block of code. Next, we have the function name. This is how we uniquely identify our function so we can call it whenever we need to. Choosing a clear, descriptive name is really important for understanding what the function does later on. After that, we have parentheses, which are essential. Inside these parentheses, we put any arguments or parameters we want to pass into the function. This is how we can give the function some input to work with. Finally, the colon at the end of the header is key because it tells Python, the function header is complete, and now the block of code that makes up the function begins. It's like the signal to start the function body. So, in summary, def starts the function, the name identifies it, parentheses hold the arguments, and the colon marks the end of the header and the beginning of the function's code. All of these elements together help us create clear, manageable, and reusable functions in our programming. All right, let's take a closer look at this example of a function. Here, we have a simple function defined with the keyword def, followed by the name message. When we call this function, it executes the code inside its block. In this case, it prints out welcome to function. This example is great because it shows how functions are used to organize code and make it reusable. Instead of writing the print statement multiple times, we just define the function once and call it whenever needed. This ties into our overall theme of understanding how to structure our code efficiently. Functions help us break down complex tasks into manageable pieces, making our programs more readable and easier to maintain. So, this is a straightforward example, but it highlights the core idea of defining and using functions in Python. So now that we've defined a function, the next step is to understand how to call it. Calling a function is pretty straightforward. Once the function exists, you can invoke it from anywhere in your program, whether that's from another function, a main program, or even directly from the Python prompt. The key is to type the function's name followed by its parameters, if it has any. The general syntax looks like function name, then in parentheses, the list of parameters. For example, if you have a function called message, you'd simply write message to execute it. Remember, this is how you tell Python to run the code inside that function. It's a simple yet powerful way to organize and reuse your code effectively. This step is crucial because it connects your function definitions to actual program flow, making your code modular and easier to manage. Now let's look at a simple example to see how functions work in practice. Here, we define a function called message. The line def message is where we establish the function's name and its structure. The comment, #function definition, just helps us remember what that line is doing. Inside the function, we have a print statement that outputs welcome to function when the function is called. And finally, we call the function with message. This triggers the code inside the function to run, and the output appears in the console. This example highlights the basic flow. Define a function, then call it to execute its code. It's a straightforward way to organize and reuse code in programming, which is a key theme we're exploring in this presentation. Let's talk about the return statement. This is used at the very end of a function, and its main purpose is to send a result back to where the function was called from. It usually marks the conclusion of the function's execution. The basic syntax is simple. You write return followed by an expression. That expression can be a value, a variable, or even a calculation. Remember, the return statement is key because it allows your function to produce an output that can be used elsewhere in your program. Connecting this to the overall theme, understanding how and when to use return helps you build more effective and modular code. All right, let's take a closer look at this example. Here, we've defined a simple function called add that takes two parameters, a and b, and returns their sum. This demonstrates how we create a reusable piece of code that performs addition. Next, we see how we get user input for these values. Using the input function, we prompt the user to enter values for a and b. We convert these inputs from strings to integers with int, ensuring that we're working with numerical data. Then, we print the result of the addition, showing the sum of A and B by calling our add function with the user-provided values. When we run this program, it asks us to enter values for A and B, and then it displays the sum. For example, if we input 10 and 20, the output will be 30. This example highlights how functions help us organize code and make it more manageable, especially when performing repetitive tasks like addition. It also emphasizes the importance of converting user input to the correct data type before performing operations. Overall, this simple program showcases fundamental concepts of functions, user input, and output in Python, which are building blocks for more complex programs we'll explore later. Now let's look at the different types of functions in Python. There are two main categories. First, we have built-in functions. These are functions that Python provides for us, so we can use them right away without having to define them ourselves. Examples include print, input, and len. These are really handy because they save us time and effort. The second category is user-defined functions. These are functions that we create ourselves to perform specific tasks. For example, I might write a function called myAddition that takes two inputs, x and y, adds them together, and then prints the sum. This way, we can customize our functions to suit our particular needs and make our code more organized and reusable. Understanding these two types helps us see the full power of Python, using built-in tools and creating our own to build more complex and efficient programs. Let's explore variable scope and lifetime. Scope essentially refers to the part of the program where a variable can be accessed. Think of it as the variable's reach within your code. If a variable is defined inside a function, for example, its scope is limited to that function. Now, the lifetime of a variable is about how long that variable actually exists during the program's execution. It's like asking, how long does this variable stay alive in memory? Understanding these two concepts is fundamental because they directly impact how your variables behave and interact throughout your program. Connecting this to the overall theme, grasping scope and lifetime, helps us write more efficient, bug-free code by knowing where and when our variables are available. Let's take a closer look at this table to understand the differences between local and global variables. First, local variables are declared within a function, which means they only exist and can be accessed inside that particular function. Once the function finishes executing, these local variables are destroyed. This makes them ideal for temporary calculations or data that you don't need beyond that function. On the other hand, global variables are declared outside all functions, making them accessible throughout the entire program. They remain in memory until the program terminates, which means they can be used across multiple functions to share data easily. It's important to remember that local variables are limited in scope. They only live as long as the function runs, whereas global variables have a broader scope and longer lifetime, making them useful when different parts of your program need to access the same data. This distinction is key to writing clear, efficient code and managing data effectively across your programs. All right, let's look at this example to understand variable scope and lifetime a bit better. We start by defining a global variable and assigning it the value 100. This means is accessible throughout the entire program unless we declare otherwise. Then, inside the function local, we create a new variable also named x, but this one is local to the function and is set to 20. When we print inside the function, it shows the value 20 because that's the local x we're referring to. After calling local, when we print outside the function, it still shows 100, the global x, because the local variable only exists within the scope of the function. The key takeaway here is that variables declared inside a function are local to that function and do not affect variables with the same name outside. This example highlights how scope determines where a variable can be accessed and modified, which is crucial for managing data in larger programs. Now let's talk about function arguments. When you call a function, there are several types of formal arguments you can use to pass data into that function. First, we have required arguments, which are the essential pieces of information that the function needs to operate. Without these, the function can't run properly. Then, there are default arguments, which have predefined values. If you don't specify a value when calling the function, it will use these defaults. Next up are keyword arguments, where you explicitly specify the parameter name along with its value, making your code more readable and flexible. Lastly, we have variable length arguments, which allow you to pass an arbitrary number of arguments to a function, useful when you're unsure how many inputs you'll need in advance. These different argument types give you a lot of flexibility in how you design and call your functions, helping you write more versatile and robust code. Let's talk about required arguments, also known as positional arguments. These are the arguments that you pass to a function in a specific order. It's important to remember that the order matters here. If you change the sequence, the function might not work as expected. The number of arguments you pass when calling the function should exactly match the number of parameters defined in the function itself. For example, consider this simple function definition: def required p, q. Here, p and q are the parameters that the function needs. When you call this function, you need to pass 2 arguments in the correct order. So if you have a and b as variables holding input values, you would call the function with required a, b. The key point is that the arguments are positioned to match the parameters, which ensures the function operates correctly. If you mismatch the order, the wrong values could be assigned, leading to errors or unexpected results. This concept ties into the overall theme of understanding how functions work and how to pass data properly. Proper use of positional arguments makes your code more predictable and reliable, especially when working with multiple inputs. Now, let's talk about keyword arguments, which are also known as named arguments. These are closely related to function calls. When you use keyword arguments, you specify the arguments by their parameter names instead of just their position. This makes your code more readable and clear. For example, suppose we have a function called info that takes 2 parameters, name and age. When calling this function, instead of passing the arguments in order, you can specify them by name. So, you'd write info with age equals age and name equals name, regardless of the order. This approach is especially useful when a function has many parameters or when you want to make your code more understandable. It clearly shows which value corresponds to which parameter. So remember, keyword arguments help you identify arguments by their parameter names during function calls, making your code more explicit and easier to follow. This is a powerful feature that enhances clarity and flexibility in your programming. Let's talk about default arguments. A default argument is basically a value that a function will assume if we don't specify one when calling the function. It's like setting a default setting, so you don't always have to define it every time. For example, in our code, we have a function called info. It takes 2 arguments, name and college. But notice that for the college argument, we've assigned a default value, which is rmdSSOE. That means if I call the function and only provide the name, like info, name equals Shaurya, then the college will automatically be rmdSSOE. However, if I want to specify a different college, I can do that too, like info, name equals Swira, college equals SCO. The function then uses the values I provide explicitly. When I run these calls, the output will show that for the first call, it prints the name Shaurya and the default college, rmdSSOE. For the second call, it shows Swira and the specified college, SCOE. So the key takeaway here is that default arguments make your functions more flexible and easier to use, especially when certain values tend to stay the same most of the time. It reduces the need to specify every parameter each time, streamlining your code and making it more efficient. This ties into the overall theme of writing clean, effective, and reusable code. Now, let's talk about variable length arguments. Sometimes, when you're defining a function, you might not know exactly how many arguments you'll need to pass in advance. That's where variable length arguments come into play. These are arguments that aren't explicitly named in the function definition, unlike required or default arguments. They allow your functions to be flexible and handle any number of inputs. For example, if I define a function like this, def variable *args, the asterisk before args tells Python that this function can accept any number of arguments, and all of those arguments will be captured into a tuple named args. Then, inside the function, I can process that tuple however I need. When I call the function with different numbers of arguments, like variable 10, 20, or variable 111, 222, 333, or even variable 11, 12, 13, 14, the function works seamlessly each time. And the output will show all the arguments passed in as a tuple, like arguments are 10, 20, or arguments are 111, 222, 333, and so on. The key takeaway here is that variable length arguments give your functions great flexibility, especially when dealing with unpredictable input sizes. They help you write more adaptable and reusable code, which ties into our overall theme of writing efficient, dynamic programs. Now let's talk about anonymous functions, which are often called lambda functions. These functions are called anonymous because they are not declared in the usual way with the def keyword. Instead of having a name, these functions are defined inline, which makes them great for short, simple tasks. You define a lambda function using the lambda keyword, and that's why they're also known as lambda functions. One key point to remember is that lambda functions can take any number of arguments, just like regular functions, but they can only contain a single expression. This limitation keeps them concise and focused. Overall, understanding lambda functions is important because they allow for more compact and flexible code, especially when you need a quick function for a specific purpose within a larger expression or function call. This fits into the bigger picture of writing efficient, clean Python code. Now let's take a closer look at lambda functions. The syntax is quite simple. Lambda followed by the parameters, a colon, and then the expression you want to evaluate. Think of it as a quick, inline way to create small anonymous functions without the formal structure of a full function definition. For example, if I write x equals lambda a times b, I'm creating a function that multiplies two numbers. In the example here, I prompt the user to input values for a and b, convert them to integers, and then pass them to this lambda function. When I run it and enter 10 for a and 2 for b, the output is 20. The key takeaway is that lambda functions are a handy way to write concise, one-line functions that you can use immediately, especially when a full function definition might be too verbose or unnecessary. This approach ties into our overall theme of writing efficient and readable code. Let's talk about something called a documentation string, or docstring for short. This is a special type of comment in Python that helps us provide more information about functions, methods, or classes. Essentially, it's a way to document what our code is doing, which is really helpful for anyone who reads it later, including ourselves. To declare a docstring, we use triple double quotes like this right below the class, function, or method definition. This is different from regular comments because it actually becomes part of the object's documentation. There are a few rules to keep in mind when writing a docstring. First, the first line should start with a capital letter and end with a period. This line is usually a brief summary of what the function or class does. If you have more details to add, you can include additional lines after a blank line, which helps visually separate the summary from the rest of the explanation. Following these guidelines makes our code much clearer and easier to understand. It's especially useful in larger projects or when sharing code with others, as it provides immediate context and helps maintain good documentation standards. Now let's talk about accessing docstrings in Python. The docstring is a special string that describes what a function or class does, and it's incredibly useful for documentation purposes. You can access this information in two main ways. First, by using the doc attribute of the object, which is straightforward and simple. Second, by using the built-in help function, which provides a formatted help message including the docstring. For example, suppose we have a function called add, and inside it, we include a docstring that explains what the function does, in this case, performing the addition of two integers. When we define the function, we can then call add_doc to see the docstring directly, or use help add to get a detailed description. This approach makes your code more understandable and helps others, or even your future self, quickly grasp what each part of your code is intended to do. Remember, well-written docstrings and knowing how to access them are key practices in writing clear, maintainable Python code. Let's talk about some good programming practices that can really improve the quality of our code. First, always use proper indentation. This makes your code more readable and easier to understand, both for yourself and others. Remember, consistent indentation helps reveal the structure of your program clearly. Next, when defining class names, start the first character with a capital letter. This convention helps distinguish classes from other identifiers and keeps your code organized. Also, avoid deep nesting of loops. Excessively nested loops can make your code complex and hard to follow, so try to keep the logic as flat as possible. Another important point is to use spaces around operators. It might seem minor, but it greatly enhances readability. For example, write a +b instead of a +b. Also, avoid using keywords or reserved words as variable, function, class, or method names. This prevents confusion and potential errors. When naming functions or variables, stick to lowercase letters. This consistency makes your code cleaner. Whenever you need to add explanatory notes, use comments or docstrings. They help clarify your code's purpose and make maintenance easier. Lastly, give meaningful names to variables, functions, methods, and classes. But be careful not to make them overly lengthy. Clear, concise names improve understanding without cluttering your code. All these practices collectively contribute to writing clean, efficient, and maintainable code, which ties back to our overall goal of writing high-quality programs. All right, so let's talk about modules. A module is basically a file that contains Python code. Think of it as a way to organize your code into separate, manageable pieces. Within a module, you can define functions, classes, and variables that you might want to reuse across different parts of your program. The key idea here is reusability and organization. To use a module, you simply import it using the import statement, like this: import module name. This way, you can access all the functions and classes defined inside that module. It's a powerful way to keep your code clean and modular, especially as your projects grow larger. Understanding modules is fundamental because they help you break down complex problems into smaller, manageable parts, making your code more efficient and easier to maintain. Let's take a closer look at the DataTime module. This is a really handy tool when we need to work with system date and time in our programs. What it does is provide us with the current date and time in a specific, easily understandable format. For example, if we write a simple code snippet, we start by importing the DataTime module. Then, we can get the current date and time by calling DataTime now. When we print this out, it shows us something like 2020-0408-1425-49, 363,535, which includes the year, month, day, hours, minutes, seconds, and even microseconds. This is incredibly useful because it allows us to track when events happen, log data, or even timestamp our results. Throughout this presentation, we've seen how modules like DataTime help us add real-world functionality to our programs, making them more dynamic and useful. All right, let's talk about the from import statement. So if you only need specific variables or functions from a module, you don't have to import everything. Instead, you can use the from import syntax. For example, if we're working with the math module and only need the square root and factorial functions, we can write from math import sqrt factorial. Then, we can directly use these functions without prefixing them with math. For instance, print the square root of 4 or the factorial of 4. The output will be the square root, which is 2, and the factorial, which is 24. This approach keeps our code cleaner and more focused on exactly what we need, making our scripts more efficient and easier to read. It's a handy way to selectively bring in only the parts of a module that are relevant to our task. All right, now let's look at how we can create our own user-defined modules in Python. The first step is to create a new Python file, and in this case, we'll name it myful, py. Inside this file, we define a simple function called message. When called, this function will print out a friendly message. Welcome to myful module in Python. The key point here is that creating a module involves writing a Python file with functions, variables, or classes that you want to reuse later. This approach helps organize your code better and promotes reusability. Remember, once you've created this module, you can import it into your main scripts and call these functions whenever needed. This is a fundamental step in modular programming, which is essential for managing larger projects efficiently. So, by defining functions inside your custom module, you're setting the stage for cleaner, more organized, and more maintainable code. All right, so now we're going to create another Python file, and let's call it test.py. In this new file, you'll want to include the code that imports your myfl module. Specifically, you'll write import myfl. Then, to access the message function inside myfl, you'll call myfl message. This step is crucial because it demonstrates how to organize your code into separate files and how to call functions across different modules. Remember, creating multiple files helps keep your projects clean and manageable, especially as they grow in complexity. This example ties into the overall theme of modular programming, breaking down your code into smaller, reusable pieces. So, by doing this, you're making your code more organized, easier to troubleshoot, and more scalable in the long run. Now, let's talk about how to run or execute the file. In this case, we're looking at the file named test.py. When you run this file, the output you'll see is "Welcome to myfl module in Python." This step is crucial because executing your script allows you to see the results of your code in action. It's how you verify that your program works as expected. Remember, the output here confirms that the myfl module is properly imported and functioning within your Python environment. This ties into the overall theme of understanding how modules and scripts interact, which is fundamental in writing effective and organized Python code. So, always make sure to run your scripts to see the real-time results and catch any issues early. All right, let's talk about packages in Python. Essentially, a package is like a directory or folder that contains Python files, which are the modules, and it also includes a special file called init.py. Now, this init.py file is really important because it tells Python that this directory should be treated as a package. So, whenever you have a directory with this file inside your Python path, Python recognizes it as a package. This concept is fundamental because packages help us organize our code into manageable, logical parts, especially when working on larger projects. It makes our code more modular and reusable. Think of packages as containers that hold related modules together, and the presence of init.py signals to Python that these modules belong to the same package. So, in the context of our overall journey through Python, understanding packages is key because it sets the stage for how we structure and import code efficiently across different parts of our projects. Let's take a look at an example of a package in action, specifically in the context of game development. When we talk about a package here, we're referring to a bundled set of tools, resources, and code that work together to streamline the development process. In game development, this might include assets like graphics, sound effects, and animations, as well as scripts for game mechanics and logic. The key point is that packages help us organize and reuse components efficiently, saving time and reducing errors. They also promote consistency across different parts of the project. By understanding how these packages are structured and utilized, we can see how they fit into the larger theme of modular and scalable development. This approach ultimately makes complex projects more manageable and collaborative. Let's walk through the steps to create your own user-defined packages in Python. First, you need to create a folder or directory where your package will reside. It's important to place this inside your main Python directory, or else it won't run properly. For example, you might name this folder mipkg. Next, within this folder, you'll create your module files. These are Python files with the extension py. For instance, you could have add, py, and sub.py, which contain functions for addition and subtraction, respectively. After that, you run your main Python program, which we'll call test.py. This is where you'll import your custom modules and use the functions you've defined. Don't forget, in the same folder, you'll need to create an init.py file. This file can be empty, but its presence tells Python that this directory is a package. Finally, in your test.py, you'll write code to import these modules from your package and call their functions. This way, you can organize your code better and reuse your modules across different projects. So, by following these steps, creating the folder, module files, the init, py, and then importing everything in your main script, you establish a clear structure for your own user-defined packages in Python. Let's take a closer look at the structure of a package. When we talk about a package, we're really referring to its core components and how they're organized. First, the key points to understand are that a package isn't just a random collection of files. It's designed with a clear structure to ensure functionality, maintainability, and ease of use. At its most basic level, a package typically includes the core code or modules, which are the main features or functionalities. These are often organized into directories or folders based on their purpose or role. In addition to the code, a well-structured package will include metadata files, like documentation, configuration files, and sometimes scripts for installation or setup. These are crucial because they help users and other developers understand how to use or extend the package effectively. Connecting this to our overall theme, a solid understanding of package structure is essential because it impacts how easily a package can be integrated, maintained, and scaled over time. When we design or evaluate a package, thinking about its structure helps us ensure it's robust, clear, and aligned with best practices. Let's take a closer look at the contents of the files and modules within this package. First, we have the init, py file. Usually we keep this file empty, but it's important because it tells Python that this directory should be treated as a package. Moving on, there's the add, py module, which contains a function for adding two numbers. This is a simple example of defining functionality inside a module. Next, we have sub, py, where we've written a function for subtraction. Again, this modular approach helps organize related functions together. Then, there's test, py, which demonstrates how to import and use these modules. In test, py, we import our add and sub modules using the package name, mipkg, and assign aliases for convenience. The script then prompts the user to enter two values, converts them to integers, and calls the addition and subtraction functions accordingly. This setup shows how modular code can be reused across different scripts, making our programming more efficient and organized. Overall, understanding these file contents and their roles is crucial for managing larger projects with multiple modules and functions. Now let's look at how the output works with this simple example. First, I entered the value of A as 100, and then I entered the value of B as 20. As you can see, the program then performs the addition, which results in 120, and the subtraction, which gives us 80. This demonstrates how basic arithmetic operations are executed based on user input. It's a straightforward way to see how input values are processed to produce the desired output, and it ties into our overall theme of understanding fundamental programming concepts. Let's talk about the Python standard library modules. This library is essentially a collection of pre-made script modules that you can easily access in your programs. The main idea here is to simplify your coding process and save you time by removing the need to rewrite common commands. These modules contain built-in functionalities that help you perform a wide range of tasks more efficiently. For example, the math module provides advanced mathematical functions, which are super useful when dealing with calculations. Then there's the array module, which handles regular expressions, powerful tools for pattern matching and text processing. The random module allows you to generate random numbers, perfect for simulations or games. And finally, modules like matplotlib and pyplot are essential for data visualization, helping you create graphs and charts to represent your data visually. Overall, these modules are designed to extend Python's capabilities and make your programming more streamlined, especially as you work on increasingly complex projects. Let's take a closer look at the Python math module. This module includes a variety of the most commonly used mathematical functions, making it incredibly useful for a wide range of calculations. For example, it provides trigonometric functions like sine, as well as functions for logarithms, exponents, and more. It also defines two important mathematical constants, pi and Euler's number. These constants come in handy when working with circles, angles, and exponential functions. In the code example, we import the math module using an alias for convenience. Then, we see some typical functions in action. The sqrt function calculates the square root of 15, which is approximately 3.87. The log function computes the logarithm base 2 of 20, giving us about 4.32. We also have the sin function, which takes an angle in radians, here 90 radians, and returns a value close to 0.89. The ceil and floor functions are used to round numbers up and down, respectively. So 2.5 rounds up to 3 with ceil and down to 2 with floor. The mod function splits a number into its fractional and integer parts, so 2.5 becomes 0.5 and 2. The factorial function calculates the factorial of 5, which is 120. And finally, we see the value of pi, which is approximately 3.14159. All these functions demonstrate how versatile the math module is, providing essential tools for performing mathematical calculations efficiently in Python. Let's take a closer look at the random module in Python. This module is primarily used to generate pseudorandom numbers, which means numbers that appear random but are actually generated by an algorithm. It's a very useful tool when you need randomness in your programs, like in simulations or games. In the code example, you can see we import the module with the alias rd for simplicity. Then, we use rd, randint, 1, 10, to generate a random integer between 1 and 10, inclusive. Notice how the output shows a number, in this case 5, which is randomly chosen each time you run the code. We also use rdrandom, which generates a floating point number between 0 and 1. In the output, you see a value like 0.7150866274864864766, which is a different random number each time. The key takeaway here is that the random module provides easy-to-use functions to generate both integers and floating point numbers randomly within specified ranges. This capability is foundational for many applications where unpredictability or randomness is essential, tying into our broader discussion on simulation and modeling in programming. Let's talk about the regex or array module in Python, which is incredibly powerful for pattern matching within strings. The core idea is that it allows us to search for specific patterns, making our text processing much more flexible. For example, using array search, we can look for a pattern in a string. In this case, we're searching for a string that starts with a W, has any characters in between, and ends with Python. If a match is found, the program will confirm with a message saying, "Yes, we have a match." Otherwise, it indicates no match was found. This demonstrates how regex can be used for pattern recognition in strings. Now, moving on to the split function in the same module. This function is useful when we want to divide a string into parts based on a pattern. For instance, if we split the phrase, "the rain in Spain," at every occurrence of the letter S, the result will be a list of substrings. This is particularly handy when processing text data that needs to be broken down into manageable pieces. Overall, these tools, search and split, give us powerful ways to manipulate and analyze text, which is a crucial part of many programming tasks. They help us find patterns, extract information, and organize data efficiently. All right, let's dive into slide 33, where we introduce SLM and specifically focus on matplotlib and pyplot. Matplotlib is an incredible library in Python that allows us to create a wide range of 2D plots from arrays. It's very versatile and widely used in data visualization. Within Matplotlib, there's a module called pyplot, which is particularly handy for plotting. Think of pyplot as your go-to toolkit for creating and customizing plots easily. It offers a variety of features, such as controlling line styles, choosing fonts, and labeling axes, all essential for making your visualizations clear and professional. What's great about Matplotlib and pyplot is their support for different kinds of graphs and plots. Whether you're looking to draw histograms to understand data distributions or bar charts to compare categories, this library has you covered. Connecting this to our overall theme, mastering Matplotlib and pyplot equips you with powerful tools to visualize data effectively, which is a crucial step in analyzing and communicating insights. So, as we progress, keep in mind how these visualization techniques will help bring your data stories to life. Now let's look at how to create a simple graph using Matplotlib. First, we import the library with import matplotlib, pplot as plt. Then we define our data points for x and y, which in this case are just lists from 1 to 7. The key function here is plt, plot, where we pass in our x and y data to generate the line graph. Finally, plt show displays the graph on the screen. This example demonstrates the basic steps: importing the library, preparing data, creating the plot, and displaying it. This is a fundamental building block for visualizing data in Python, and understanding this process is essential as we explore more complex visualizations later on. Now let's talk about how to format the graph to make it clear and visually appealing. On this slide, you see some example code that shows how to do that using Matplotlib. First, we import the library with import matplotlib, pplot as plt. Then we create two lists, x and y, which contain our data points. In this case, both lists are simply numbers from 1 to 7, making a straight line when plotted. Next, we plot the data with plt, plot, xy. To add some clarity, we label the axes plt x-label, x-axis, and plt y-label, y-axis. These labels help viewers understand what each axis represents. We also add a title to the graph with plt, title, my first graph, which gives context at a glance. Finally, we display the graph with plt, show. The key takeaway here is that formatting the graph, through labels and titles, is essential for communicating your data effectively. It's not just about plotting points, it's about making your graph informative and easy to interpret. This step ties into our overall theme of creating clear, impactful visualizations. All right, let's take a closer look at how line styles can really enhance our plots. In this example, we're importing the Matplotlib, pplot module as plt, which is pretty standard. Then, we define our x and y data points, which in this case are simple lists from 1 to 7. When we call plt, plot, we're not just plotting a line, we're customizing it quite a bit. Notice the color parameter, we're setting it to red, so our line will stand out. The line width is set to 5, making the line thick enough to be clearly visible. Now, the key part here is the line style, which we've set to dashed, represented by. This helps differentiate this line from others if we add more later. We also add markers to each point on the line using the marker parameter, which here is O for circles. The marker size is set to 10, making them prominent without overwhelming the line. Then, we add labels to our axes and a title to give context to the graph. Finally, plt show displays the plot. The main takeaway here is how combining different style parameters allows us to create visually appealing and informative graphs. Customizing line styles, colors, and markers helps us communicate our data more effectively and makes our visualizations much more engaging. Now, let's take a look at how to create a scatter plot using Matplotlib. This graph will display individual data points, which is helpful for visualizing relationships or distributions. The code begins by importing the pplot module from Matplotlib as plt, which is a common convention. Then, we define two lists, x and y, each containing 7 values. These represent the coordinates of the points we want to plot. The plt scatter function takes these lists and plots each pair as a point on the graph. To make the chart clearer, we add labels to the x-axis and y-axis with plt, x-label and plt, y-label respectively. We also add a title with plt, title. Finally, plt, show displays the plot. The key takeaway here is that scatter plots are straightforward to create and provide a clear visual of how two variables relate to each other. This technique is particularly useful when exploring data patterns or outliers. All right, let's talk about NumPy, also known as numerical Python. It's a powerful package in Python that's specifically designed for array processing, which makes handling large datasets much more efficient. When we refer to arrays in NumPy, we're talking about collections of homogeneous elements. That means all the elements in a single array are of the same data type, which helps with performance and consistency. You can create these arrays in NumPy using various data structures like lists or tuples, which are familiar from basic Python programming. This flexibility allows you to convert your existing data into NumPy arrays easily, making your data manipulation more streamlined and efficient. Understanding arrays is fundamental because they are at the core of many numerical computations and data analysis tasks in Python. By mastering how to create and work with arrays in NumPy, you're setting a solid foundation for more advanced data processing and scientific computing. All right, let's take a look at this example of using NumPy. First, we import the library with the alias np, which is a common practice and makes our code cleaner. Then, we create an array called T1 using the np array function, passing in a simple list of numbers from 1 to 4. When we print this array, the output shows the label array followed by the array itself, which is displayed as 1, 2, 3, 4. This example highlights a few key points. First, NumPy's array function allows us to easily create arrays from lists, which is fundamental for numerical computations. Also, notice how straightforward it is to generate and display arrays, making NumPy a powerful tool for handling data efficiently. Connecting this to our overall theme, understanding how to create and manipulate arrays is essential because many advanced operations in data analysis, machine learning, and scientific computing rely on this foundation. So, mastering this simple example sets the stage for more complex tasks ahead. All right, let's take a look at slide 48. Here, we're exploring how to create NumPy arrays from Python lists. First, we import the NumPy library using the alias np, which is a common convention. Then, we define a simple list called LSD with 3 elements, 11, 12, and 13. Next, we print out the type of this list using the type function, and as you can see, it confirms that LSD is a Python list. The key point here is that lists are versatile but not as efficient for numerical operations as NumPy arrays. So to convert this list into a NumPy array, we use the np array function, passing in our LSD. This creates a new array object, which we store in T1. When we print T1, you'll notice the output shows the array elements in a different format, with spaces separating the numbers. This is the NumPy array structure. Finally, we check the type of T1, and it shows as a NumPy end array. This distinction is important because NumPy arrays support a wide range of mathematical operations and are optimized for numerical computations, which makes them essential in data analysis and scientific computing. Overall, this slide highlights how easy it is to convert a Python list into a NumPy array, and understanding this process is foundational for leveraging NumPy's powerful capabilities in your projects. All right, let's look at how NumPy handles arrays created from a tuple. Here, we start by importing NumPy as np, which is the standard convention. Then, we define a tuple called tup with 3 elements, 11, 12, and 13. When we check the type of this variable, it clearly shows us that it's a tuple. That's our starting point. Next, we use the np array function to convert this tuple into a NumPy array, which we assign to the variable T1. When we print T1, it displays as an array with the elements 11, 12, and 13, but notice how it's formatted differently from a tuple. Finally, we check the type of T1, and it shows us that it's now a NumPy array. This example highlights a couple of key points. First, how easy it is to convert a tuple into a NumPy array, and second, how NumPy arrays provide a different, more flexible structure for numerical computations. This process is fundamental because it allows us to start with simple Python data structures and convert them into powerful NumPy arrays that are optimized for mathematical operations and data analysis. Let's take a closer look at the reshape function in NumPy. This function is really useful because it allows us to give a new shape to an existing array without changing its data. So, it's all about reorganizing how the data is structured, not altering the data itself. For example, suppose we start with a simple list, like 11, 12, 13, 14, and convert it into a NumPy array. When we print that array, it appears as a one-dimensional array with all 4 elements. Now, using the reshape function, we can transform that array into a 2 by 2 matrix. This means we're changing the shape from a single row to a 2-row, 2-column structure. Notice how the data remains the same, but the way it's organized visually changes. This concept is really important because in data analysis and scientific computing, we often need to reshape data to match the input requirements of different algorithms or to make the data easier to interpret. So remember, reshape is about rearranging data's structure, not its content, which makes it a powerful tool for flexible data manipulation in NumPy. Now let's take a closer look at the NumPy arrange function. This is a built-in function in NumPy that helps us generate arrays with evenly spaced values over a specified range. Essentially, it allows us to create sequences of numbers quickly and efficiently. For example, if we write import numpy as np and then create an array with np, arrange, 0, 10, what we're doing is generating numbers starting from 0 up to, but not including, 10. When we print this array, the output will be a list of numbers from 0 through 9, like this. 0, 1, 2, 3, all the way up to 9. This function is really handy because it simplifies the process of creating numeric sequences, especially when you need evenly spaced values for calculations, plotting, or data analysis. Connecting this to our overall theme, understanding how to generate such sequences is fundamental in working efficiently with data in Python, and NumPy's arrange makes this task straightforward and fast. All right, let's talk about pandas. Pandas is actually the most popular Python library used for data analysis, and it's a tool that many data professionals rely on daily. The name pandas comes from the words panel data, which hints at its strength in handling multidimensional data sets. One of the key features of pandas is that it allows us to represent data in a very familiar spreadsheet-like format. Think rows and columns. This makes it much easier to manipulate, analyze, and visualize data efficiently. As we progress through this presentation, you'll see how pandas fits into the bigger picture of data analysis workflows, making complex tasks much more manageable. All right, let's talk about how data is represented in pandas. Essentially, pandas provides us with 2 main structures. The first is a series, which is one-dimensional. Think of it like a single column of data, similar to a list or an array. It's great for holding a sequence of values with an associated label or index. The second structure is a data frame, which is 2-dimensional. You can think of it as a table or a spreadsheet, with rows and columns. This is incredibly useful because it allows us to organize and manipulate data in a more structured way, making it easier to analyze and visualize. Understanding these 2 key representations is fundamental because they form the backbone of working with data in pandas. Whether we're dealing with simple series or complex data frames, knowing how data is structured helps us choose the right methods and tools for analysis. This ties into the overall theme of mastering data manipulation efficiently and effectively. Now, let's look at the output series to understand what a series in pandas actually is. As you can see here, the series is represented as a one-dimensional array-like structure. It contains homogeneous data, which means all the elements are of the same type, in this case, floating point numbers. The code snippet demonstrates how to create a series. First, we import pandas with the alias ped. Then we define a list of data points, 1, 1, 1.2, 1.3, and 1.4. We pass this list to the ped series function to create our series object. Finally, we print it out with a descriptive message. The key takeaway here is that a series is a simple yet powerful data structure in pandas, which allows us to handle one-dimensional data efficiently. Understanding this concept is fundamental because it forms the basis for working with more complex data structures like data frames later on. So, in the context of data analysis, the series is like a labeled, ordered collection of data points, making it easier to manipulate and analyze your data. Now let's look at how we can create a series using a dictionary. As you can see in the code, we first import pandas as ped. Then we define a dictionary where the keys are 1, 2, and 3, and the corresponding values are petrol, diesel, and LPG. When we pass this dictionary to the PED series function, it converts the dictionary into a series object. The resulting series will display the keys as the index and the values as the data. This is a very straightforward way to create a series when you already have data in a dictionary form. It highlights how flexible Pandas is, allowing us to easily convert different data structures into series, which are fundamental for data analysis. So, this method is particularly useful when your data naturally comes in key-value pairs, making your workflow more efficient and intuitive. All right, let's talk about data frames in Pandas. As you can see from the slide, data frames are essentially two-dimensional structures that allow us to organize data in rows and columns. Think of it like a spreadsheet or a table in a database, very intuitive and flexible for data analysis. When we create a data frame, we typically import Pandas with the alias PED, and then we can initialize an empty data frame using PED, data frame. If you run that, you'll see an empty table with no columns or data, just as shown here. This structure is fundamental because it forms the basis for most data manipulation tasks in Pandas. Whether you're importing data from files, filtering, or analyzing, data frames are at the core. So, understanding how to create and work with them is key to leveraging the full power of Pandas in your projects. Remember, it's all about organizing your data efficiently to make analysis straightforward and effective. Now let's look at this example of creating a data frame in Pandas. You can see that we start by importing Pandas as PED, which is a common convention. Then we define a dictionary called dict1 where the keys are A and C, and the values are the fuel types, petrol, diesel, and LPG. Next, we create another dictionary named data, which has a single key, call1, and its value is the dict1 dictionary. When we pass this data dictionary into the Pandas data frame constructor, it creates a data frame with one column named call1. The data frame's rows are populated with the values from dict1, so A corresponds to petrol, B to diesel, and C to LPG. Finally, when we print the data frame, it displays these fuel types alongside their labels. This example highlights how Pandas allows us to organize and display data efficiently, which is fundamental when working with datasets in data analysis. It connects to our overall theme of understanding data structures and manipulating data effectively using Pandas. All right, as we wrap up, I want to point out some valuable resources to continue your learning journey. One great website is Programiz.com, specifically their Python programming section. It's a fantastic place for beginners to get hands-on tutorials and practice exercises. Another helpful link is the Python Wiki, which offers a comprehensive beginner's guide for new programmers, covering everything from setup to more advanced topics. These resources are perfect for reinforcing what we've covered today and exploring Python further at your own pace. Remember, consistent practice and utilizing these resources will really help solidify your understanding and skills. So, don't hesitate to revisit these sites and keep experimenting with Python. Thanks for your attention, and happy coding.